In this video, we're going to talk about substitution and elimination reactions in allylic and benzylic systems. So why does the allylic or benzylic system matter? Well, let's look at intermediates. In general, when you look at an organic reaction, most, but certainly not all reactions, feature such intermediates as carbocations, carbanions, or radicals. We talked a whole lot about carbocations in the work you did in first semester. Later this term, we're going to get into Allylic chemistry. We're going to talk a lot about carbanions. And then, of course, radical chemistry. There's lots of free radical chemistry, like the bromination reactions that we talked about. So the interesting thing is that all three of these intermediates, carbocations, carbanions, and radicals, they're all more stable if you put it into an allylic system because you can delocalize the positive charge, the negative charge, or the radical. Same thing about a benzylic system. If you turn these things into benzylic systems, again, that delocalization makes all three of these more stable. And this is going to influence the rates and sometimes the products of reactions. So let's look at a first example. This is a simple Sobolysis reaction. A Sobolysis reaction is when an alkyl halide reacts with its solvent. And in this particular case, I have just up here, I have a simple halide reacting with a water ethanol mixture. You make some alcohol, you make some ether. Now here are four candidates. Which of these would be fastest in a Sobolysis reaction? Now last semester you learned that the tertiary reactions were fastest in Sobolysis reaction. This is SN1 reactions, whereas primary reactions were terrible. Primary halides were terrible. So what about these allylic ones? Well, they both are allylic, but which would be faster? Well, let's actually look at the data. If you look at the data, you'll find that the allylic one over here with the chloride on the tertiary center is by far the fastest one. So this carbon is all set to do Sobolysis. It's tertiary, but it's also allylic. And so if you look at it, it's 162 times faster than simple tertiary. Interesting thing is this one over here, which is primary but allylic, is 38 times faster than tertiary. And the pure primary one, it doesn't react at all. When it says less than, that means they couldn't find any reaction and they just got tired of waiting. So they say less than this 0.00002. So look at this. So the general message is allylic is by far the fastest, and if it's tertiary allylic, fastest of all. Okay, so let's look at this a little more detail. So what's the product going to be? So if we do this reaction, well, there are two products. Okay, I've given the secret away here. But what are the relative amounts? You're going to get you can get the primary alcohol. You can get the tertiary alcohol. Which one are you going to get the most of? Well, in the final result, if it's driven by thermodynamics, you're going to make the most stable molecule. Which of these is the most stable? Well, one is the most stable. Okay, so the most logical conclusion is you're going to get 1 and 2, and 1 is going to predominate, but is it going to predominate completely? I mean, is it going to be like 99 to 1, or is it going to be 50-50? Well, the facts say it's under the conditions where I took this experiment anyway, from the literature, it was 85% of the primary one. The main determining factor is not the fact that the OH is primary, but the fact that the double bond has more substituents. So that's an 85% record. So what's the actual mechanism? Well, the water, of course, takes this N carbon over here and pushes that chloride out. So let's look at the opposite example. What's going to be our major product now? Well, okay, so if it's driven by thermodynamics, we expect the same result, correct? If it's delivered by kinetics, determined by kinetics, then perhaps we get a different result. But these Sobolysis reactions were slow, and generally speaking, they're going to get thermodynamic products. So we still expect one. But now how about the ratio? You ought to be able to tell me exactly what the ratio is. That is, if you can remember about 3 minutes ago, when we put up the previous result, is it's still 85-15. Why do we get the same percentage from a different reaction? Well, let's look at this energy profile here. Is that in terms of reactivity, the tertiary is more reactive, and mainly because it's less stable to start with. This one has the more substituted double bond, and it's a more stable molecule. And so this one reacts faster because it's closer to its transition state than was the primary one. So the tertiary reacts faster, but the intermediate for both of these is identical. So they're going to the same place. So there's no difference in energy once you get here, and there's also no memory of where you started. So since you're at the same intermediate, the second step has to get the same product mix no matter what. And the energy of the more substituted double bond is lower than that of the less substituted bonds. Now these things aren't to scale; they're just made up spacings. But they'll show you what's going on. Is that once you have a common intermediate, your product mix isn't going to depend on where you started from. So that's kind of interesting. So these allylic Sobolysis reactions really are different than you'd normally expect. More stable reactant reacts slower. Common intermediate, products must be the same. And in terms of drawing arrows, the chloride just leaves to give this common intermediate, and then the water either attacks that carbon directly to give this product, or the water attacks out here to give the product on top. I really should have used two colors of arrows, but I think you can see what's going on. Okay, let's look at a standard SN2 reaction. Okay, the standard SN2 reaction, what would you expect? You'd expect the sulfur to come, kick out the chloride, and to give the sulfur here on the end. This is a faster reaction than you normally get. And why is it faster? Well, it's faster because the intermediate here, the 5-coordinate intermediate, is also stabilized by the double bond. So it turns out that allylic primary, this is a primary allylic group like this one is actually a substitution reaction is faster than are normally. So SN2 reactions are actually faster than use back. Now what about product 2? Would you expect to get some product 2 over here? Well, you could, but nevertheless, because of this one here is primary and it's faster, that one actually is pretty much going to go as a standard SN2 reaction. But let's look at this one. This one here can also can undergo a completely different reaction. This one, the sulfur could attack the secondary position, and indeed it might be a little bit faster than the normal secondary position, but we know the secondary reactions are generally, reactions of secondary halides are generally slower than that of primary halides. So it turns out in this particular case, the main product actually is not this one. I'm sorry, not 2, not the secondary one, but this one here where you get the primary halide. So the secondary allylic one gives you the same product as we had on the previous slide where we also got that product. So this is called an SN2 prime. This is called an SN2 prime reaction, and the key thing is it's faster than a secondary SN2. This is a little bit. I kind of made this more confusing than it should have been. When we had that, in the previous slide, let me go back. In the previous slide, we have the chloride on the end. Normal SN2 proceeds, and because there's not that much steric hindrance. Primary reactions are normally faster than one at a secondary position. This 5-coordinate transition stable actually gets stabilized. So pretty much the only product is product 1. When we change it around, put the chloride over here, it's still an allylic. Now what happens, you turn around, you get the SN2 prime reaction, and 1 remains the primary product. But now the reaction mechanism is what we call SN2 prime. And SN2 prime, the prime just simply means we're not attacking the carbon with a halide directly. We're attacking your mode carbon. And so this is kind of a cool reaction. Okay, what about benzylic reactions? we have various products here. We can imagine a substitution reaction here. We can imagine an elimination product here. So what are we going to predict as the two products? Well, with hydroxide, we always have to worry about the difference between elimination and substitution. And it turns out that the substitution reaction is indeed faster than normal, and so that's a really good reaction. The only problem with that is that the elimination reaction also is much faster than normal. And in this particular case, the double bond that we make is more stable than normal because the double bond is conjugated to the phenyl. So what wins on this? Elimination really wins. This would be a difficult reaction to do up on top. If you need to do this up here, what you'd want to do is do a Sobolysis reaction, an SN1 reaction, to give you that alcohol. So this is going to give you elimination, not substitution. And what about if you move the halide out here to the end? Well, out here in the end, the substitution reaction is a normal. There's no particular rate of it's just a normal SN2. But look at this elimination. It's more favorable than normal because that hydrogen's more acidic because it's stabilized. The anion is stabilized by the phenyl ring. So this is more reactive yet. So again, elimination is vastly in favor. So these benzylic ones, they really want to do elimination, not substitution. So the predicted product would be definitely the elimination product. So there you go. That shows you how complicated these things can get when you add that. It's actually not really that more complicated. You just have to remember it's different. Here, I want to show you one last example, which is in the textbook. Make a Grignard reagent of an allyl system. This would be the same if you made a lithium reagent. Similar things happen. Make a Grignard reagent. And now we're going to react it with the epoxide. Well, it turns out there's two products. Why are there two products? Well, because there are two Grignard reagents. So how does this work? This is your expected Grignard reagent. But it turns out that double bond can reach over, grab the magnesium, and these two Grignard reagents are actually in equilibrium with one another. This is not resonance. This is pure equilibrium. That magnesium can flip back and forth depending on which carbon it is on. And this simply means now that when you do your reaction of your epoxide, the epoxide can add to the magnesium on the end, or it can add to the magnesium in that secondary position. So this is pretty wild, and just tells you some of the fun things you can do with allylic and benzylic systems.